Good morning, everybody. Thank you for joining us today. My name is Ronaldo Pinto. I'm the Technical Sales Director for Applied Flow Technology. My email is ronaldopinto@aft.com, and I'll be hosting today's webinar, which we have named Raise the Bar Using Vacuum Breaker Rolls. If you have any questions during the webinar, please type them in the GoToWebinar chat room, and at the end we'll have a session of questions and answers where I'll try to answer all your questions. And if we don't have time, you'll receive an email with the answers to your questions. So what are we going to cover today? We'll have a brief introduction addressing the scope of the webinar. Then we'll talk about how does air get into your system, effects of trapped air in your system, how to handle air in pipelines. We'll be talking about air valves, the different type of air valves and where to locate them. Then we'll be talking about modeling air valves using AFT Impulse, the considerations and some tips. And then finally, we'll apply all these concepts to an AFT Impulse example. And finally, we have conclusions and questions, a session of questions and answers, as I mentioned before. So we know that free air can be found in most piping systems. And trapped air in pipelines may cause many problems, such as poor flow, water hammer problems, poor pressure control, damaged pumps, and broken pipes. The safe and efficient operation of a liquid piping system may depend on the continued removal of the system. You cannot let the air accumulate there, and we'll see the problems that would cause. So in this webinar, we'll discuss the effects of air and their sources in the piping system. And also we'll discuss the different type of air valves and their recommended location according to the AWA C512 standard. And finally, we'll apply all these concepts and analyze their effect in a piping model using AFT Impulse. So how does air get in your system? Well, initially, the most critical one is when your pipe is in a system is initially being filled. When it's empty, it's full of air, and the liquid of your system starts pushing downstream the air, which can be released through hydrants, faucet, or other mechanical devices. If these means of air are not efficient, air will be trapped and it will travel to high points in the pipeline. A second source of air in your system can be drawn through your pumps, or it can be drawn into your pipe under vacuum conditions. A third source of air in your system is when your pipe is drained, air enters the pipe. Another source of air in your system is, by nature, the water contains approximately 2% dissolved air or gas by volume at standard condition. This dissolved air in the pumps can come out of the solution in different parts of your system where turbulence, hydraulic pumps, and other locations where pressure variation phenomena occurs. Once it comes out of the solution, air and wastewater gases will not readily dissolve back into the water, and it will collect in pockets at high points along the liquid piping system. So what are the effects of trapped air in your system? Air in pipe system is in the form of bubbles. These air bubbles will migrate to the high points on the system. If provisions are not made to remove this air from the high points, pockets of air will collect and grow in size. So here we have your pump. We have the bubbles traveling up to and forming the pockets right at the high points of your system. Air pockets will grow. Air pocket growth will then gradually reduce the effective liquid flow area, creating a throttling effect, the same as if you had a partially closed valve. In some cases, it can be so severe that air can create and block totally the water flow in your pipe. So here we have the bubbles traveling up to the high points, forming the air pocket, and the air pocket restricting the flow area in your system. As we said, it can grow so much that it can totally block the flow of water in your system. Also, trapped air can contribute to water hammer problems, pipe wrecks, and system noise. Pipe corrosion is accelerated when exposed to air pockets, which can result in premature failure of your pipe. It can cause erratic operation of your control valves, meters, and equipment. It can increase the energy consumption of your pumps because when you restrict the area, it will take more energy for it to pump through those pockets. We have talked about the presence of air, but the absence of air can be a problem too. Temporary pockets of air may be needed in special circumstances to prevent vacuum conditions after the pump trips or surge conditions. Vacuum conditions should be avoided as they can result in collapse or deformation of thin wall pipe. This is especially critical for big diameter pipes. Here we have a pump trip, and the column water reverses down to the pump, and it creates a pocket, a vacuum that can collapse your pipe due to surge problems. Also, contaminants can be sucked into the system. This is especially critical in the food industry. So how do we handle air in pipelines? As we have seen, air entrapped in pipelines can cause many problems, but also there are situations where air has to be taken in, primarily for efficient drainage, vacuum protection, or surge protection. In conclusion, the most efficient way to control your air is by emitting or releasing large or small quantities of air whenever it is required. So now that brings us to air valves. Air valves are hydromechanical devices designed to automatically release air in waste and wastewater gases or emit air during filling, draining, operation of the liquids piping system for water and wastewater services. Air valves are more common on water system, but rarely found in non-water systems. Why? Well, in the case of petrochemical application, introducing air in the system is not allowed for safety reasons and risk of combustion. Adding air sometimes can make the system more susceptible to corrosion. Adding air into the system that is not subsequently released can alter the performance of your pumps and can increase the energy consumption. Air valves are generally misnamed as air release valve, or frequently they're also called vacuum breakers, but the correct name for them is air valves. As you can see in the last version of Impulse, we changed the name. There are three types of, according to the American Water Works Association, AWA, standard C512, there are three basic types of air valves. Automatic air release valve with small orifice, air and vacuum release valve with large orifice, and the combination of both, which is called combination air release valves. So let's take a look at each one of them and how they operate, because it's crucial to understanding how to model them in AFT Impulse. Automatic air, let's see the first type, automatic air release valves with small orifice. This type of valve is designed to automatically release small pockets of accumulated air from a pipeline while the system operates under pressure. How does it operate? Small quantities of air accumulate in high points of the pipeline where the air valve is located. The pressurized air valve expels the water in the air valve, and the descending water level moves the air valve main float with it. At a certain position, the main float pulls down the small seal that partially opens the orifice. The pressurized air can escape, and the water level rises again, reclosing the orifice. So here we have the air release valve with small. This is a graph. In this case, here we have the floating device of the valve, we have the seal, and we have the small orifice. At this point, the water is full, the pipe is full of water, so it's pushing the floating device up. When the air valves, dissolved air starts to accumulate, it fills the chamber, the upper chamber of the valve with air, and it starts pushing the floating device down. This releases the sealant and opens the orifice. And here it's totally open, so it releases the air bubbles or the pockets, the air bubbles accumulated in the air valve through the small orifice. Very important, and this you have to keep. Air release valves are intended not to release air as it accumulates at high points during system operations. They are not recommended for vacuum protection or vent large volumes of air when filling large diameter pipelines, because they inherently have small orifices. These valves are not designed to protect your pipeline from vacuum. They're only designed to release small amounts of air, of the air that accumulates, undissolved air that travels up to the high points. When vacuum protection is necessary, air release valves may be used in conjunction with air vacuum valves, or you can use the combination valves that we'll be using in the model. Now let's see the second type of air valves, air vacuum relief valve with large orifice. These valves are designed to exhaust large quantities of air during pipeline filling and to emit large quantities of air when the internal pressure of the pipeline drops below atmospheric. In other words, they're designed to release a large amount of air when filling your pipe and emit also air for vacuum protection. Once the pipeline is purged of air, the valve closes tight and does not open again until the system is drained or negative pressure occurs. So the difference between the first pipeline, the first air valve, is that this one does not open during operation. The first valve does open during operation to release small quantities of air. How does it operate? It has two modes of operation. First mode, it discharges air at high velocity when the pipe is being filled. When the water arrives to the valve, the flow rises and closes the outlet. The second mode of operation introduces air into the pipeline when the internal pressure is subatmospheric. In other words, when vacuum occurs. So here's the valve. In this case, the pipe is full of water. It has a large orifice, and the orifice is closed because the water is pushing the floating device up. When you're filling the pipe or vacuum occurs, the floating device goes down. The upper chamber is full of air. It pushes the floating device, and air is allowed to be released or admitted. As we will see in the model that we will be working with, air vacuum valves can be equipped with anti-slam devices which controls the flow of water into the valve to reduce the surges in the valve. The anti-slam device is useful at high points when the column separation or rapid changes velocity occurs. It's the same thing when you have check valves. If it slams, close, or open, it creates spikes of pressure that make the surge problems worse. So the same as check valves, the air vacuum relief valves can be, you can request to have an anti-slam to reduce the surge problems created by the slam of the floating device when it closes too fast or it opens too fast. So now we have the combination air release valves. This combination, this type of valve combines the two previous valves that we have described, the function of them. Combination air valves are designed to perform the same function as air vacuum valves and air release valves. It has three modes of operation. First mode, it discharges air at high velocity when the pipe is being filled. Second mode, it introduces air into the pipeline when the internal pressure is subatmospheric. In other words, when vacuum occurs. And third mode is releasing strained air from the pipeline at high points of the pipe. So it releases small amounts of air when the bubbles to avoid the formation of the pockets at the high points. So here we have the combination of air relief valves. In this case, it's full. We can see that it has two orifices, a small orifice here and a big orifice at this point. And the floating device is being pushed up by the pressure of the water. The salt air, when it starts accumulating at the high point, it starts accumulating in the upper chamber, so it releases the seal that closes the small orifice. So it releases a small amount of air. When large amount of air is accumulated when you're filling the pipe or vacuum occurs, the whole system is pushed down and the big orifice is released. So these are the two functions that it is. The first function is releasing small amount of air while the pipeline is in operation, and the other one is from vacuum releases or emits large amount of air when pipe is being filled or vacuum occurs. Where do we locate these valves? Well, the AWA has a recommendation. It's followed by most valve fabricators. Here we have the different locations suggested to use different type of air valves. I'll mention three that I consider important. First, air vacuum valves. It's used at the pump discharge. This is to avoid, to help with surge problems with negative pressures that can collapse your pipe. Combination valves at high points, it's very critical. Here it's used to release small amounts of the bubbles that travel to the higher points, or release big amounts when vacuum occurs or when you're filling the pipe. And air release in horizontal, you might have a long horizontal run of pipe at the higher points, and you might need intermediate release of air to avoid to release the bubbles that accumulate there. Okay, so this brings us to modeling air valves and AFT Impulse. AFT Impulse can help engineers to identify vacuum conditions if they'll be present in your system and help properly size the air valve to protect the pipeline when these events occur. Here are some considerations to keep in mind when modeling these type of valves to best represent their complex behavior. Okay, so let's start. Air valve property windows. Here's the air valve property windows that will be you need to fill. So you need a minimum information to be able to run it. First, the valve type. You have to define the valve type that you're going to use, whether you're going to use a vacuum breaker, you're going to use a combination, you're going to use a air release, etc. External gas properties, that's another information that you have to fill. And valve orifice information that you get from the supplier. So let's talk about a little in detail of each one of them. Valve type. AFT can model 4 types of air valves. Vacuum breaker and release valve. That's how Impulse call it, and the equivalent to the C512 standard would be the ones they call air vacuum release valve with large orifice. Second type is the gas release. That's how Impulse call it, and the equivalent to this, the ones we saw previously used by the C512 standard, they call it automatic air release valve with small orifice. Then we come to the combination. Combination valves is called by Impulse vacuum breaker and 2-stage gas release. As I said, the C512 standard calls it combination air release valves. There's a 4th type of air valve that AFT Impulse model not mentioned in the AWA standard, which is the vacuum breaker valve. Also called sometimes vacuum venting valves or vacuum limiters. They are valves which allow air to be aspirated once vacuum occurs. These valves are installed in pipelines, vessels, machines, and equipment, and are used for venting tanks or limit the vacuum in your system. Here we have an example of our vacuum breaker valve used at the discharge of the pump to protect them from surges. The green are the vacuum breakers, and here is the check valve. So the vacuum breaker is protecting the pipe from the surge, the vacuum created by the surge conditions. External gas property. As we saw, it's a minimum information that you have to place. The gas properties are used to model the external gas at the valve orifice. This is commonly air at atmospheric condition, and it will be set by default on the valve windows. Valve orifice, CDA. The area of the orifice will be provided by the manufacturer. However, the manufacturer will often not provide the discharge coefficient. This value will be needed to be estimated and is typical between 0.6 and 0.9. So to get this value, you might have to contact the manufacturer, or there's a white paper on our website which provides a in-depth discussion on how to calculate this value using different standards or equations equivalent in the industry. Before we go to the model and Impulse, there's some analysis assumptions that you have to take in consideration when you model your Impulse, air valves and Impulse. First, the calculations assume that all the air entering and exiting the system in the valve remains in the orifice, and that air does not enter the valve from other areas in the pipeline. AFT Impulse will not account for potential movement of air pockets through the system. This means that care should be taken when choosing the location of the air valve junction in the model. The valve behavior will be defined based on the neighboring pipe computational stations. It will not model the air pockets formed in other parts dragged by the fluid to the high points. So here we have AFT example that we'll be working on. We have a tank that had a 30 feet head of head we had a pump, we have a pump, we have a check valve, and we're pumping up a storage tank that is located at 400 feet with two intermediate elevations, one at a high point of 390 feet and another lower point of 30 feet. All the pipes are 4 inches standard. And so what do we want? For the system below, we want to determine, first, type of air valve most suitable to protect the pipe. How does the air valve selected operate in a pump trip? And how does the air valve selected operate in a startup? We want to check both events to make sure they work properly. So step one, when you do your model, run your model in steady state to make sure that everything is in order and there's no possible source of artificial transient. These steps are important for any impulse model. You have to make sure that the steady state makes sense and there's no source of artificial transient, because artificial transient will not let you AFT impulse model run. So here we have a model. I created a scenario that for steady state. And how do we run the steady state? We come to tools, analysis, and we say analysis type of simulation, steady state only. So it's not going to consider the transients. I have already run this model, so we go to the output results. We see there's no warnings. The pump is operating normally. Here's the diagram, the operation system, the operation closed. The pipes do not have negative flow, etc. So first step, we say, okay, the steady state is good. Now, we want to create a pump trip scenario. Look for possible points of where vapor volumes form. So let's see that first. We have a pump trip. Scenario. Here, we want to check if there's problems with high points, with vacuum created. When we pump trip the pump, we're tripping the pump in 0.5 seconds to 70%. And with tripping it totally, we're stopping the pump in 1 second. So now we look at the results. It's telling me that I have vacuum conditions at the station 0 in pipe 3 and station 49 in pipe 7. This is telling me that I'm having pockets of surge problem right here at the vicinities of the high point. So let's look at that graphically. We go to the graph and we see, okay, let's see pump 7. Pipe 7. What are we looking at here? We're looking at vapor volumes form in the pipe 7. That's the one entering the high point. And we're looking at the pressure static. So we see the vapor formation, the vapor pockets formation. And And here we have the surge problems. And when the vapor pockets collapse, they have a spike of pressure that creates surge problems and makes it more critical. So we have subsequently more air pockets forming. So we need to do something. We need to do something because we have air pockets forming, and we need to be able to control that. So the next step is to create a pump strip scenario with an air valve. Select an air valve type following our recommendations. So we're going to create an scenario with an air valve to see how it works. So we added an air valve. And now we have to select the type of air valve we want. So here is the guidance. We are in an upper point. We're in the upper point here. So we want to select a combination air valve. And what type of air? So we look for a catalog manufacturer, and we're going to select the combination of air valve, which has small orifice and a big orifice. And here are the dimensions that we're going to select. The small orifice has 0.02 inches square inches on the small diameter, and in the big orifice it has 0.49. So that is our first selection. So we come to the air valve. We select a combination, which is the fourth one, vacuum breaker and 2-stage, and we put the dimensions that the fabricator said, 0.49 for the big diameter, the big orifice, and 0.02 for the small orifice. As I said, we run it already. It's already run. So we check if the air pockets disappear. So we're going to check the pipe 7 transient to see if the pockets are still showing up. So now we see that we don't have any more the air pockets. So the air valve is working. We still have some pressure spikes here, and we have a big pressure spike here in this case. So let's find out what's happening here. If cavitation is predicted at the valve, the following warning will appear. We'll check for this warning. This warning means that the vacuum breaker most likely is undersized for your system, since gas flow in the valve was not able to prevent cavitation. Cavitation at the valve could lead to damage in the system and the water hammer. So let's check for that. So we go to the output, and we see the warning. Junction 22 is cavitating. So let's see what's happening with the air valve. We go to the graph, and we see how the air valve is operating. So here's the valve operating. In the lower graph, we have the gas volume in the upper chamber that's accumulating in the air valve. And here we have the mass inflow. We can see in the first graph that it's releasing the air, it's opening and it's closing, but it's not releasing it totally because it's accumulating air in the valve. And when finally it gets to release it, it creates a spike of pressure that we can see in the pipes connected to the valve. Let's see the transient in pipe 7. So here we see the high spike of pressure that's created when the air pocket is finally released. So evidently, this air valve is working, but it's undersized. So what are the solutions? First is increase the air valve, the size of it. Also, you can request the air valve to be equipped with anti-slam device. Another solution could be you could slow down the pump trip, make it less severe. In this case, we went to an extreme of closing and went totally in 1 second. You might say, okay, let's slow down the pump trip to avoid this problem. Another solution that you can have is reduce the pump speed to levels that the air valve can handle. I created 2 scenarios reducing the pump speed to reduce the flow, 94% and 84%. Let's take a look at those scenarios. So I'm going to see how the air valve operates. I'm going to compare scenarios. (94% and 88%. We say select. Takes some time to bring the graphic, but comparing 3 scenarios. Okay, so here we have the ones that we initially saw. The same air pocket. If we reduce the speed of the pump to reduce the flow, we see that the pockets are, the air valve is able to handle better. It forms less pockets, the pockets are less small, but still it's a problem. So let's see what happens when you reduce the pump speed to 88%. We see the pockets are very small, and we see the valve operating in a much better way. And it closes, so it's able to release the air. And let's see now the pump transient problems. Let's go to the scenario where we have a lower speed. Let's go to the graph results and see the transients created. So now we see the transients created by the surge pressure is more handleable. We can handle better. It goes from 125 to the upper one that would be around 250, which makes, so this might be the pipe might be able to handle this. And if you want to avoid the spikes of pressure, you might request the valve to have the anti-slam. So 3 possible solutions. one is cheaper than the other, and like increasing the size of the valve might be a solution, or slow down the pump trip, or reduce the pump speed to reduce the flow. Okay, so now we want to check the startup. What do we have in the startup condition? In the startup conditions, you will have this pipe partially full, and we have to include that in your model when you do the pump trip. So when you do the pump startup. So when you're creating a pump startup, you have to consider, these are 3 tips that you have to comply. Use the optional tab in the pipe connected to the air valve to define the percentage of air present in the startup when the startup is initiated, the air present in your pipe. So here, in the pipe connected, in this case, pipe 7, we tell it has 30% of liquid. Input the initial gas in the air valve. You also have to input the amount of air that's going to be released that is present in the air valve. If you don't do that, you won't be able to graph how the liquid fills in the pipe. And third this is for all the check valves. You have to check, generally check valves create artificial transients unless you, in the initial condition and the optional conditions, tell it that in the special condition, it's closed in the steady state and allow it to open in transient. So let's see that in the model. First, the air valve. No, first the pipe. Here is the valve. So we go to the optional tab and we tell it that it's 30% partially full. It means it has 70% of air. Then we go to the air valve. Here we tell it the mass of air that's in the pipe. This is if we want to model how the pipe is being filled. And finally, to avoid artificial transient messages, we go to the optional tab in the check valve and we tell it in initial condition that it's closed in steady state and that it's allowed to open in the transient. Okay, so as I said, I ran all these cases. We'll check the messages. Well, cavitation, we have the cavitation message, which is typical, and it's telling us another message that we should model the pump trip using, oh, by the way, let me show you how we're tripping the pump. Of course, this is an extreme pump trip, transient. We're shutting out the pump is tripping in 2 seconds, partially 1 second, 25%, 1.5 seconds. So these, but the idea is so you can see the failure and see the air valve operating. There's an important tab in the output that is event messages by junction or event messages by time. So here you can check what's happening at each time, what event messages are occurring, and how the air valve is operating, the same as a check valve of any element in your system that operates during the transient. So let's look at how the air valve is operating. So here we see the air valve releasing air. It comes to a point that it releases the whole air of the pipe and it closes, and then we see some surge cases of the. So here is when the pipe at exactly 6.28 seconds, the pipe is being filled, and this is when the air valve closes. So now let's look at the pump filling parameters. So here we're looking at the liquid distance along the partially full pipe. This is how it goes. And this is the liquid percentage. So we see that we start with 30%. And then at 1.9 seconds, it starts releasing air, it releases air, it releases air, and then it totally releases the air in 6.23 seconds. Okay, so apparently it's working, but let's look at the pump transient to see how, if there's any surge problems. And we're looking at pipe 7, the one connected to the air valve. We see a big spike problem here of 1,000 and above 600 psi. So we say, okay, the air valve is releasing it, but still there's problems of surge pressure because it's not releasing the air fast enough, and we might have to, we need to do something. So what are the solutions for the surge problem that we're observing? First, and this one would be the most logical one, is to slow down the pipe, how you fill up the pipe. Here, as we saw, and how do you do that? Well, reducing the speed of your pump to much slower startup, so it will fill the pipe. Right now, it's filling it up in 7 seconds. So you don't need that fast, and we'll create any scenarios where you'll fill it slower, and we'll see the effects. Request an air valve to be equipped with the anti-slam or increase the size of the air. But as I said, the most logical one would be the first one because it's the cheapest, and we'll fill in it too fast. So let's look in a scenario where we're filling up slower. Here we go to the transient tab, and we see that I'm slowing it down. The pump is at 0 second, 1 second, 2%, 2%, and it stays at 121 seconds. So let's see the effect of filling it slower to see if it benefits and it reduces the surge problems. Let's see how the air valve is operating. So we can see that the valve is operating, is more logical, it's less critical, it's filling the pipe in 33 seconds. So let's see the pipe filling. Taking some time to ring it. So the pipe is being filled in 33 seconds. Longer time, but still we can increase it because there's no need to fill the pipes really fast. But let's see the transient, if it improves the response of the system to filling it slower. So let's compare that with the filling it. The scenario comparing it with the filling it faster. I'm going to select the pump startup with the initial one we saw so we can compare the results. Taking some time. Okay, so now we're comparing the scenario. Let's see. The spike of 1,000 disappeared, so it's less critical. So it's still filling up in 33 seconds. We saw that filling up slower improved the reaction. The air valve had time to react faster. So I would say that I would fill it up slower, and it will improve. Like 33 seconds is a short time to fill up a long pipe. It can even take half a day. So probably modeling a slower fill up of the pipe will allow the air valve to react and release the air without causing surge problems. Okay, so conclusions. The most efficient way to control the air is admitting or releasing large or small amounts of air whenever it is required. And that is what air valves do for you automatically. AFT Impulse can help you properly size your air valve to protect the pipeline for different scenarios, filling up the pipe and for surge problems. When using air valves, the most important to consider is type of air valves. You have to select properly. We saw the guidance in the AWA and the C512 standard. Use it. Location, it is important where you locate it. Proper sizing the valve. You have to make sure that, okay, it's acting properly, it's releasing the air, but also that it's not causing surge problems. And again, the last one is once you size your air valve, you have to make sure that it's not causing air problems, surge problems. Thank you so much for joining us. It was a pleasure having you. Hope you see you in next webinars, and I hope the information was useful for you in this webinar. Thank you again.